All right, we're going to try this again, um, hopefully with sound this time. So the next lesson is angles and triangles. It's called Developing the Sine Law. And then the next lesson is going to be the sine law. So we're going to probably tie the two together because neither of them are particularly long. So at the beginning of this, we looked a little bit at some of your right angle trig stuff. So again, labeling your triangle, the sine of an angle is equal to the ratio of the opposite side divided by the hypotenuse. So that's the first one. So again, sine is opposite divided by hypotenuse. The cosine of an angle is equal to the ratio of the adjacent divided by the hypotenuse, and the tangent of an angle is equal to the opposite divided by the adjacent. The other thing that we didn't explicitly review, but that you should know um, from your previous math courses, not just 10C, but you would have seen it before, is Pythagorean theorem, a squared plus b squared equals c squared. Again, your C side is going to be your longest side or your hypotenuse, and the squares of the other will be equal to the square of that. So make sure you understand that one. I think you guys already saw that kind of in that last section as well. So, it says review of right angle trig from 10C. So again, so doa. The other thing as well um, that we didn't explicitly talk about is just kind of labeling our triangles. I guess I can just make it colorful here. You guys don't me. I want colors. So draw a triangle ABC. So if we are to draw a triangle ABC, so again ABC would be our vertices for it, A, B, and C. And one thing that you would have done in 10C that I guess we haven't really explicitly said is sometimes you can label the sides. So in some of the previous questions, I would have called this side line segment AC, because again, that's the segment between point A and point C. The other way that we could actually label it, you see how I used capital letters at all of the vertices here? The other way that you can actually label it is the side that's across from it, the lowercase letter of that. So this would be, again, across from B would be side B, and across from, meaning not touching it, opposite to it, side A, or angle A would be side A, and then C's a little bit harder, so I usually make it, a cursive C or something that you can tell the difference between those two C's. Um, so again, opposite, so capital letters for the vertices. I don't know that there should be an I there. I don't know how confident I feel in either of those. And then lowercase for the sides. And you use the letter opposite the vertice. Letter from opposite. So write the definitions and draw a diagram to illustrate the angle of elevation and the angle of depression. So these are terms again that you would have seen. So our definitions, actually, you know what I might do? Just give me a second. Whoop. All right, so I have my key open just because I have a nice diagram and I have it already written all there for us. So you might need to pause it for a second. Oh, how do I scroll? There we go. Um, so our two definitions, you might need to pause it to write this down if I go too fast. So the angle of elevation is the angle between a horizontal line or the line of sight. Oh, sorry, a horizontal line and the line of sight when looking up. Angle between line of sight. Sorry, I'm just trying to, oh, I can't draw on here. So looking, hopefully you can see where my cursor is. This would be the line of sight for this individual. So if there was a bird in a nest in the top of the tree, the angle of elevation would be from that horizontal up to where you would be looking at that bird. So that's your angle of elevation. The angle of depression would be the angle between a horizontal line and the line of sight when looking down. So you're standing at the edge of a cliff and you see a little boat there. So your angle of depression, again, the horizontal between your line of sight and towards wherever you're looking when looking down. So elevation is looking up, depression is looking down. Hopefully you can equate those pretty easily, right? Feeling down when you're depressed? Yeah, that's true. Okay, so the next one I usually actually have you guys do, but since you don't have protractors, we're just going to kind of look at the one that I had drawn in my book. So it says, draw a right angled triangle with one 30-degree angle, label angles A, B, and C, and accurately measure all the side lengths. So just to, I'll come back to this, but just to look at what we would be doing. So a right angle triangle. So what you know you would need if you were drawing this, right angle means you need to have a 90-degree angle. So it'd be something like this. And then it's saying 130-degree angle. So what I would probably do is kind of line up my protractor. I don't think I can pull it out right now. There is a smart protractor, but I don't know how to. Can you hear that motorcycle? There's a motorcycle ripping. Um, so I would grab my protractor and use the little markings to figure out how to draw a 30-degree angle. I'm probably not at all right on this, but I might draw it like that. And then I would go through and erase my leftover. Nope, it's not gonna let me do that. Of course it's not. Nothing, hey? Nothing. All right, it's not even gonna let me do that. So I would use pencil in real life. I'm not sure why it's not letting me erase that portion. So what I would be trying to goal to have, again, it's saying a right angle triangle, 90 degrees here. You need a 30-degree angle, and we know angles in a triangle will add up to 180 degrees, so we know that this angle should be 60 degrees. And usually when you guys try to do this, we get pretty close. The 90 is kind of the easiest one to do, and then usually people kind of get like in the range of maybe 28 to 32 degrees, and this would be 58 to 62 degrees. And the more accurate you are with these measurements, usually the better the data actually ends up. And we'll use the data that I did on my practice one. So I drew a triangle, and this is what my triangle looked like. So again, I labeled my sides as A, B, and C. And what you see, you can draw this without actually measuring it. It's not a big deal. You don't have to have the exact things, but we can just use the numbers that I have in here. So if you measure the one that is in my book, this portion, the measure from B to C, or we could call that side length A, is 5.2 centimeters. And so I tried to go as accurately as possible, right? I can't go to the nearest hundredth or anything like that, but I can do the nearest tenth because my ruler that I used had little tick marks for millimeters. So that's 5.2 centimeters. So my 90-degree angle is at angle C, and my side that's opposite angle C, that I'm representing there, it is 10.4 centimeters. And then my angle B is 60. 30 was the other one that we needed, right? So 30 is right there. So my angle B is 60. I think if I measured them, I was pretty good. I got pretty close on all of those. So side length B is 9.0 centimeters. So I drew it. I felt pretty proud. I measured it. And then what it's saying is verify the following statement based on your triangle. So you might want to pause and just draw this down on here because I'm going to actually go back to my smart file, but let's use this triangle for our example. Nope, nope. Okay, so now it says verify the following statement based on your triangle. So we're going to do it based on the triangle that I had drawn there. So it's saying, sorry, we can't use any of this stuff. You might need to rewind back, but looking at B, so this is side length B, side B, and this is angle B, right? capital for the angles, lowercase for the side length. So it's saying side length b divided by the sine of b. So it's just asking, let's look at that ratio. So if I do b divided by the sine of b. So in the diagram that I had, side length b was 9.0, and the sine of b, so angle b was my 60 degrees. So one thing is, in your calculators, you need to make sure you are in degree mode. Guess I probably didn't remind you of that previously, but hopefully when we did those practice sine, cosine, tangent questions at the beginning, you realized if you had something wrong, if you had a weird answer, but you need to make sure you're in degree mode. So TI's, it's second function mode. Casio, I think you go to your main screen and you scroll way down to setup. I don't have one in front of me, so if you can't find it, let me know and I can ask Corey where it is in the Casio. She knows better than me. So oh, I meant to write the sine of 60 here, not just b again. So you probably need to put, I don't know if you do, no harm in doing it, put brackets on the bottom there. It should be okay though, as long as you close your brackets if your calculator opens one up. And so what I get when I just type that in, I get 10.39. There might be more decimal places. I don't remember where I rounded it. And now if I go side length c divided by the sine of c. So you can see kind of in the font with this. This is a lowercase c. This is an uppercase c. I can't do that as easily writing, so I do my cursive. So side length c, if I look at that triangle, that was the longest side. That was the 10.4. And angle c was my 90-degree angle. So if I type that in, so the sine of 90 is equal to 1, so I know this is going to be 10.4. And then for, just for good measure, I'm going to try the same thing with a. So lowercase a on top divided by the sine of a. So side length a was at 5.2 centimeters. And angle a, sine of 30. So 5.2 divided by the sine of 30 gets me 10.4. I truly hope you guys can hear that motorcycle because it's ridiculous how loud it is. Okay, so with this, so we see these are basically this one, it would round to 10.4. Maybe this angle wasn't exactly 60, or maybe this measure wasn't exactly 9.0. Maybe it was 9.03 or something like that, or 8.995. But you can see that it's essentially equal for all of those ones. So this is kind of a verification. It's not a proof. It's taking a specific example and seeing if this is true. So what we can see is for the triangle that we drew, not that one, this one, for the triangle that I had drawn, that ratio of b divided by the sine of b equals c divided by the sine of c was true. Again, just a bit off due to that measurement error, but pretty darn close. So what we're going to see now is we're going to prove why that's true in every case. Not just a verification, but now we're going to prove why it's true in every case. And so proving the sine law. So using the triangle below, use a two-column proof to prove this. So what we want to do is prove that that ratio is equal no matter what the case is. You notice in this question, we don't have any measures, right? We don't, no angles, no side lengths. We don't have numbers for it. So we're proving that it's true no matter what. So our little two-column proof, I don't know if I'll be able to write small enough in here, but we'll do our best. So we see that we're really not given much information in this, right? I have whatever angle B is, I have whatever angle A is, I have whatever angle C is, and then you see we've labeled some sides. So side length B is across from angle B, side length C is across from angle C. We could label this whole thing as side length A. It's not important in this question. So I'm just going to erase it because it's already getting messy enough here. And then we have kind of a long line segment BC point D. So again, from our vertex down here, that's perpendicular. So there's a 90-degree angle here. We know that line segment BC is a straight line, so this would also be a 90-degree angle. We'll probably come to that in a little bit. But this is definitely important in this proof, is your right angle triangle ratios. So what I'm going to start with in terms of my statement, and again, you're not going to have to do this proof. I'm just proving that the sine law is true so that we can use it, right? We want to know if we don't, you guys are actually very willing to just accept that whatever I say is true. But in this unit, especially after we just did logic, let's prove why it's true in every case. So what I'm going to start with is the sine of angle B. So, oh, sorry, I meant to label on this triangle. This we're going to call, so this length, I'm going to call it side length X. I can't really call it side length B because I've already labeled this side length B, and I can't really call it side length C, so I'm just going to call it X. So if we're looking at kind of this little triangle, I could look at my ratios to find whatever that angle B is. And so we know this, if we're looking for the sine of an angle, it's equal to the opposite divided by the hypotenuse. So if I'm looking again at the triangle that I have now made very purple, the little triangle, the opposite side to angle B would be side X. So if I were to label just for my purple triangle, this would be the hypotenuse, always across from the right angle. This would be my opposite, and this would be my adjacent side. So that's just for that little purple triangle that we have. So if I wanted to know the sine of angle B, it's again opposite divided by hypotenuse. It's going to be side length X divided by C. We've labeled that side C. And so again, you see we have no numbers here. I'm not pulling out a ruler and a protractor. I don't need numbers. I'm just looking at that ratio. So my reason or my justification or my proof is our definition of sine equals the opposite side divided by the hypotenuse. And so now what I'm going to do is I'm going to rearrange this formula to solve for x. So if I just wanted to get x by itself, I know I need to multiply both sides by c, because right now I have x divided by c. So if I'm rearranging this formula to solve for x, I need to multiply both sides by c. So c times the sine of b is equal to x. So rearrange the above equation to solve for x. All right, nothing wild I've done now. Now what I'm going to do, because you guys know how I feel about this, is I'm going to be considering the other triangle. Oh, come on, green. It's your time. I'm going to consider this triangle now. So I'm going to be looking at the other small-ish triangle. And now what I want to do is talk about the sine of angle C. So again, our definition for sine is opposite divided by hypotenuse. So if I'm looking at my purple triangle, this is my reference angle, B is going to be the hypotenuse. This, again, now for my green triangle, this is still going to be the opposite, and this would be my adjacent side. So the sine of angle C is equal to the opposite divided by the hypotenuse. we got this is our definition of sine equal to the opposite divided by hypotenuse, those side lengths. And now I'm going to do basically the same thing. I'm going to rearrange to solve for x in my green equation here. So rearranging to solve for x, I need to multiply both sides by side length b. So b multiplied the sine of c is equal to x. And so now, again, we've seen this before. We have two things that are equal to the same thing. So, sorry, I'm just going to add one thing in here just because it is slightly confusing. Just because it kind of looked like capitals. So these should both be lowercase c's here. This is a uppercase c, right? That's the angle. So those two are the lowercase c's. Okay, so back to where I was. So these are both equal to x. So we know if they're equal to the same thing, we can set them equal to each other. So we would have seen that. Called that the transitive property. So we can set them equal to each other since they are both equal to the same thing. So now what I'm going to have is c times the sine of b equals b times the sine of angle c. Glad I left the rest of this page blank, hey? Running out of room. And so now what we have, so we have side length c multiplied by the sine of b is equal to side length b divided by, or sorry, multiplied by the sine of angle c. And so now I know what I'm going to do for this step, I'll write it out here first, is I'm going to divide both sides by sine of b and sine of c. So I'm gonna scroll myself down a little bit and then I'll write it up here appropriately. So c times the sine of b equals b times the sine of c. So again, I'm going to divide both sides by the sine of b. I'm going to divide both sides by the sine of c. What you do to one side of the equation, you have to do to the other. And so what we see is we're going to get some nice cancellation here. So sine of b divided by sine of b is equal to 1, and sine of c divided by sine of c is equal to 1. And so now what we would have is c divided by the sine of c is equal to b divided by the sine of b, which is what our original thing asked us to prove. It had it like flipped left and right, but that's still the same thing. So be a friend, so I just wanted to represent what I was saying here, down here, just so you can see if I divide both sides by the sine of b, it's going to cancel on this side. If I divide both sides by the sine of c, it's going to cancel on this side. And so what we end up with, again, is c divided by the sine, sorry, lowercase c divided by the sine of c equals lowercase b divided by the sine of angle b, which is what it was asking us to prove. And so from here, so we've proved the sine law. And so I think this isn't super long yet. It's long, but we can manage. We'll just have a big lesson. Um, we're going to go on to the next lesson, so where we actually start using the sine law. So we've proved it, but now let's look at kind of some of the applications. So this is on to the next page in your notes package. So 20-2, the sine law. I'm actually slightly panicking that it's not working again, so I'm going to actually save this one and start the next one. So you'll probably want to move on to it right away.